We're going to express the same position in many different forms. First, let's define it in Cartesian coordinates to be at 3, 4. Now let's write this in vector notation. X equals 3i plus 4j. Where I is a unit vector in the x direction and j is a unit vector in the y direction. Now let's write this in eastings and northings, compass directions. It's 3 east and 4 north. Now let's write it as a bearing, and let's assume that the distances are in kilometres. For a bearing, the y-axis is north, and we need to work out the angle around clockwise from the y-axis. We use Pythagoras' theorem to work out that the distance from the origin is 5, and the angle theta is given by inverse tan of 3/4, which is equal to 36.87 degrees. So in bearings, this is 5 kilometres at 0.37 degrees. Now let's write this in polar coordinates, r theta. Again, we need a distance from the origin and an angle. This time the convention is that the angle is measured from the x-axis in an anti-clockwise direction. Again, the distance r is 5 kilometres, but this time the angle is given by inverse tan of 4/3. Which is equal to 53.1 degrees. The convention in polar coordinates is also that the angle is measured in radians. There are 360 degrees in a circle and also 2 pi radians. So to convert to radians, we have theta is 53.1 divided by 360 times by 2 pi, which equals 0.927 radians. So in polar coordinates, we have r is 5 and theta is 0.927. Finally, a very small change in angle can mean a very large change in position if your distance from the origin is large. For that reason, we often measure angles to a high level of accuracy and write them in degrees, minutes and seconds. There are 60 minutes in a degree, there are 60 seconds in a minute. For example, the angle inverse tan of 3/4 correct to the nearest second is 36 degrees, 52 minutes and 12 seconds.